All right, so this video is covering the notes on section 1.1, which is linear equations. We're suggesting that you read through page 88 to kind of look at some ideas that we, are going to assume that you already know. Also, when you finish this video, you should go on to the next video. I generally lump section 1.1 and section 1.2 together on the same day. I think I'll break up the videos separately here on 2 videos, but you should just know that I always do one section 1.1 and section 1.2, which is the applications of linear equations, on the same day. So if you're looking at this because you were out sick, make sure that you cover both of those videos. Okay. So linear equations. So this is what we refer to as a degree 1 equation. That means that we have a variable x to the 1 power, not squared. So the x is going to be raised to the first power. So in a 1 variable, it has the following form. So we have ax plus b is equal to 0. We have a lot of different forms. This is just one form that we have. And then where the a is going to be the coefficient and b is going to be a constant, right? So we have, if you wanted to write it as ax to the 1 plus b, that would be fine too, equals 0 if it's an equation. So we have a degree 1. So that's a linear equation. In the future sections, we'll also have another term out here where we'll have x squared, and that will be a quadratic equation. So because we don't have a squared term here, we refer to this as a linear equation. Okay. And then, of course, a and b just can't be 0. Well, b, I guess, could be 0. It would still be a linear equation. But a certainly could not be 0. Okay. All right. Which of the following 4 equations is a linear equation? So pause the video, write down linear, not linear, or whatever the case is. All right, so this first one, the x has an exponent of 1, and so yes, this is linear. It just has a square root of 2 as the constant, and that's fine. That doesn't affect the x having a degree of 1. All right, next one. This one is not linear because it's not x to the 1. We learned in previous chapter that square root of x could be written as x to the 1/2. And so it doesn't have a degree 1. It has like a half a degree, which is not even a thing. We don't call it a half degree. So this is just not linear. So no. Not nonlinear. All right, next one. This one, if we expanded it out and moved it all, we could certainly get it into this form, and the x's would all have a degree 1. So this one is linear. And then this one. This one is not linear because that x is downstairs. So this we could write as 2x to the negative 1. Right, minus 5 equals 4. So that is not a linear because this does not have a degree 1. It has a negative 1 is the exponent. And so this is nonlinear. Okay? All right, so let's solve. Example 1 is asking you to solve. So solve that equation. Again, pause this and then work on it and then watch the video. Okay, so the first thing we want to do is probably distribute. So we get 6x minus 12 equals, and then here we'll distribute the negative 7 minus x minus 5. Combine like terms on this side, combine like terms on this side. Ultimately, we want to move the x's to one way and the non-x's to the other way. So let's move this x over, so that'll give me 7x. Now, some of you would be doing the following. Oh, we're going to add x to this side and add an x to this side. Eventually, you will have to get over that and just say, oh, it's negative over here. I'm going to move it to this side. I always move my variables in the direction that would give me a positive leading coefficient, if I can do that. So I'm going to move this. The sign changes, and I'm adding it to the other side, and so I just jump to 7x. This 12 goes to the other side. Well, first of all, let's add these two things up. That's going to be a 2. And that 12 goes the other side, which is going to make it positive 12. And so plus the 2 that's over there, that gives me 14. So you should be able to do some of that movement in your head instead of writing out every little step. As we get into more and more complicated mathematics, we want to be able to do some of these things in our head. And then I divide both sides by 2. And again, I'm not going to say divide by 2, divide by 2. I'm just doing, divide by 7, divide by 7. I'm going to do that in my head. So I'm going to divide both sides by 7. And so that just gives me x equals 2. Okay, now we can check that answer by plugging it into the original problem, and we will see that this side will be equal to that side if we plug that in and check our answers. That's the good thing about equations, is you can generally check your work, check your solution. Does x, if I put in x equals 2 in for each x value, is this side of the equation equal to that side of the equation? And the answer would be yes. All right, next one, example 2. So the example for this one, so pause your video, try it, and then we'll see how you do. All right, so for this one, we have a bunch of fractions. So I think it would be best to multiply through by what would be the least common denominator of all of these. So think about what that would be. And I think you would, if you think about it, you're going to multiply this side by 12 and this side by 12. And that will clear out all of the denominators. So when I multiply by 12, I'm not going to distribute the 12 to each of these things. Well, instead, I'm going to think about when I multiply this part of the fraction, this fraction by 12, I'm going to reduce the 3 with the 3 and the 12, and 4 will be left to distribute to these two things. And so that would end up, if you want, you can maybe write that out. So 4 times 2x plus 4, and we'll distribute that in the next one maybe. And so when I distribute the 12 to this fraction, the 2 and the 12 reduce, leaving me with 6 times that x. And then on the other side, similar thing. This 4 is going to cancel with the 4 in there, leaving me with a 3 times the x that's there. And then minus 84, because 7 times 12 is 84. Okay, so I would probably have already simplified these, like this thing here, but it's not bad to go ahead and do it in another step. So we have 8x plus 16 plus 6x equals 3x minus 84. All right, so I'm going to combine these these x terms. That's 14x. And I'm going to bring the 3x over, and that's going to be subtracting. The sign's going to change. So that leaves me with 11x. All right, so I have 84 and I have 16. I'm going to take that 16 over. It's going to change signs to negative. I'm going to add it to this negative 84. That's going to leave me with negative 100. Okay, and then my final answer, x is equal to negative 100 over 11. And generally, fractions are perfectly good answers, right? You don't have to turn it into a mixed number. Improper fractions are perfectly fine. And again, you could check your answer by taking this value and plugging it into your x's, and both sides of the equations would be equal. All right, the next part. When we have linear equations, we have 3 different possibilities. And so we could have what's called an identity, which means the left side and the right side are identical. So we call it an identity, and it doesn't really matter what x value I plug in. If I plug the same x value into both sides, this side will be equal to this side. And we can see that if we distribute, right? If we distribute that negative 2, we get negative 6x plus 10 equals negative 6x plus 10. All right, so now it's obvious that it's an identity. So once you get that, you know that your solution is all real numbers. Any value of x you plug in will work. So sometimes we'll write that as like a fancy R. We'll do like a paragraph symbol, but we'll make it into an R. So those are symbols that represent all real numbers. All right. We'll have a way of doing it where it says everything from negative infinity to infinity. That's another way of writing all real answers. All right. And we'll talk more about that in future sections when we talk about how to denote solutions in set notation, in interval notation. All right. The next one, that's conditional. So we'll have only specific solutions, generally one solution, if this is the case. So you can see if you solve this, you move the 5 over to the side, that becomes 9. We end up with 3x equals 9, and then divide by 3. So we would have x equals 3, so we get generally one solution, and I take that answer and plug it in. The left side will be equal to the right side. All right, and then the last one is a contradiction. So no x value that I put in here would make the left side equal to the right side, right? So the left side will be x, the right side is x minus 2. There's no way those two things could ever be equal. So if we solved this thing without really thinking about it, we might move the x over. So I have x minus an x, so that's 0 equals negative 2, and that's a contradiction. 0 is never equal to negative 2. So as a result, we know this is a contradiction and there is no solution. So the no solution would be something like this, the null set, or we can say the empty set. Okay? All right. A. So solve that equation. And you'll note there's 3 examples in this, A, B, and C, and there are 3 different ones. So each one of these will be one of those 3. Okay, so solve that. Again, pause the video, do all 3 of these, and then unpause the video. All right, so I'm going to go ahead and solve these. So that's a negative 2x minus an 8 plus 3x. And then if you wanted to, you could bring those over, minus an x, and then negative 8, right? So I'm going to bring the x's to the left and maybe take the constants to the right. So I'm going to take this 8 to the other side. So that's going to, or you know what? Let me leave that for right now. Hang on. Let me leave this. Probably be obvious in a second. X minus 8. So let's leave it the right-hand side alone. And then let's just simplify the right-hand side, the left-hand side. So I'm going to add negative 2x with 3x. So that's x minus 8 equals x minus 8. And you can see we have an identity, right? The same thing on both sides. If we went ahead and solved it, you would say subtract x from both sides and add 8 to both sides. And that would be 0 equals 0. So either way you want to think of it, if you get the same 2 numbers, like let's say we subtracted the x from both sides, we get negative 8 equals negative 8 would be another way of doing it, and just leaving the constants alone. So negative 8 is equal to negative 8. That's an identity. All right, so that's this situation here. So what you should do is say, okay, all real numbers. And so that will be your answer, all real numbers. So that's like an R, a double-lined R, almost like a paragraph symbol, like you've seen in English class, paragraph symbols like that. We just do it and turn that into an R. Or like a little script DR, something like that. All real numbers. All right, next one. This one's pretty easy. I'm going to add 4 to both sides. So we get 5x equals 15, and then divide by 5x equals 3. So that's our one solution. Okay. Now our books sometimes in solutions set like this, they'll say like the solution is x such that x is equal to 3, right? I mean, that's like a real formal way of writing it, but we're perfectly fine with just saying x equals 3. Okay. And then the next one. So let's distribute that. That's 8x minus 2 equals 8x plus 5. And if I bring the 8x over, that cancels out, and we're left with negative 2 equals 5. And that's a contradiction, right? So there's no x value that I could plug in here that would make this side equal to this side. So this is no solution. Or the null set. You could do this as well. Don't put the null set in the empty set. That doesn't make sense. So one or the other. Or you could just write out no solutions. would be acceptable as well. Okay? So let's look at literal equations is the next thing. So this is an equation that maybe like a formula that you've seen in science class, where you don't have values that are going into the variables, right? It's like the formula for the area of a circle, right? Formula for the area of a circle. Area equals pi r squared, right? That's like a formula. So I could take that thing and rewrite it. And right now it's solved for A, but I could also solve it for R, right? So it's taking an equation or a formula, if you will, and rewriting it for a different equation. So this equation is how you convert between Fahrenheit and Celsius. Right now it's solved for Celsius. But could we take this and rewrite it so that F is by itself instead of the C? So we could take and multiply through by the reciprocal of this fraction, move it to the other side, so I could have 9 over 5 times C equals F minus 32. I don't really need those parentheses in that case, but so I've taken and multiplied by the reciprocal of the coefficient, and that cancels it out on the right side, and I have 9/5 on the left side. And then I could add 32. So we could say, and then, F is by itself, so let's write it first. So I'm going to add 32, and that gives me 9/5 C plus 32. So it's the same literal equation, except now we have it solved for F, whereas this one was solved for C. Right? So if you have a bunch of Fahrenheit temperatures and you want to convert them to Celsius, you would use this formula. But if you had a bunch of Celsius, you don't want to plug it in and solve it a bunch of times. We solved it once, and now we can plug in a bunch of Celsius temperatures and get the Fahrenheit. Okay? All right, so do that. For the next 3 examples, take each equation and solve it for the variable indicated. So solve this for t, solve this variable for this equation, this literal equation for k, and solve this one for y. So try all 3 of those, and then pause the video, and then try them, and then unpause. All right, so for this one, it's pretty straightforward. We're simply going to try to get the t by itself, so I'm going to divide both sides by r. So we have d over r equals t, but generally we'd like to put the t by itself first. And so t is equal to d divided by r. All right, and this one, solve for k. Now the problem is there's a k here and here, so I can't just move stuff to the other side or divide through. So really what I want to do is I want 1k. So the trick for this one is to factor a k out of r, and you get r squared plus rl. This, I think, is the the surface area for, this looks like something for a cone, I think, but I'm not sure what that formula is for, but anyway, so I have 1k now, which is good, right? I had 2 k's, I had a k here and a k here, but now I have 1k. I want to get this k by itself, so I divide by the parentheses. So, and let's rewrite it as k over by itself. Bring this over, so s divided by r squared plus rl. Okay? And so that is that formula solved for k. All right, now to do the next one, solve this one for y. Notice we have a y here and a y here. I think what we want to do first is maybe distribute that 2 on the right-hand side. So we have 11y plus 8 equals 8y plus 10w minus 6z. Again, we're solving for y. So even though these are variables, I mean, they're going to take on some value at some point. So we kind of think of them as constants. So this 8 comes over, and let's take the 8y to the left and just the 8 to the right. So this means we're taking all the terms that have y's in them to the left. Everything that doesn't have a y in it goes to the right. So I'm going to subtract this 8y from both sides. So that leaves us what? 3y. And then we take the 8 over. So 3y is equal to, let's say, 10w minus 6z plus 8. And then we simply want to divide by 3. So y on the left is equal to, and we can just do all this. If each of these things were divisible by 3, I would probably go ahead and divide each one by 3. But since they're not all divisible by 3, I'm just going to leave it as one big fraction. Oh, wait a minute. I think I made a mistake here. This is plus 8. This should become negative 8 on this side. All right, and then divide that by 3. So 10w, 6z, and then divide that by 3. Okay. So that would be our, the literal equation solved for y. All right, so simple interest. Now this is overly simplified. We're going to have a much better formula later on, but in this section in the book, they sort of introduce this idea of simple interest. Okay, so a man borrows $2,500 to buy a new kitchen appliances. He will pay off the loan in 9 months at an annual simple interest rate of 6%. How much interest will he pay? And so we're using just this formula. The interest is P is the principal, R is the interest rate, and T is time, always in years. So the interest. So just, I know this is an overly simplified formula. We're going to have a much more complicated formula that we'll use later on, but for now we're just going to use this. So how much interest does he pay? I is the interest, and so the principal amount he's borrowing is $2,500. And we're just sort of assuming that he's just paying this, the interest is sort of like once a year, kind of, like, at the end, how much did he pay in the interest? And it's like one interest payment sort of at the end. Kind of think of it that way. It might be easier for you to think about it. And so the interest rate is 6%, but we got to write that as a decimal always. So 0.06. And then how much time? Well, it's 9 months. But we have to write that as a fraction, so 9/12 of a year. We have to write it as how many years. So it's the dollar amount borrowed, the interest rate, the annual interest rate, and then the number of years. So 9/12 is the number of years. And then we would just, in this case, just pick up a calculator. And then we would not expect you to do this without a calculator. Just a little bit tedious to multiply all that. So he would pay $112.50. And again, this is an overly simplified formula for interest. We'll use, and when we say simple interest, that's the key. Simple interest, we're just going to use this formula. We'll have a much more complicated formula later on. All right, so these are the homework for this section. Remember that this is every fourth problem, right? Times 4 just means every fourth problem. And then also remember that if you're looking at this video, Mr. Rogers probably went over the next section in this class. So make sure that you're going ahead and looking at section 1-2 video as well.